The Greeks thought there were 4 basic elements: earth, air, water, and fire. As time passed, more and more elements were discovered, and by the 20th century, they numbered almost 100. Yet for all their diversity, all the elements owe their existence to a trinity of subatomic particles: neutrons, protons, and electrons. Like hydrogen, each element has many energy states. But for chemical properties, the most important is the lowest, the ground state. And the ground states of all elements follow the pattern of the excited states in the hydrogen atom. That state of affairs comes about because of 2 very peculiar quantum mechanical properties of the electron. One is the fact that the electron has spin. Not that it literally spins like a little Newtonian sphere, but it does have an intrinsic angular momentum, just as if it did. Its magnitude is a bit less than h bar, and its vertical component is exactly 1/2 h bar. And just like the angular momentum of an orbital, the spin angular momentum can be found with equal probability in any direction along a cone. That cone and its vertical projection can point up or it can point down. Those are the only possibilities. Nothing in between is allowed. The second quirk also has to do with the electron's quantum mechanical inner nature. No 2 electrons can ever have exactly the same quantum state. In other words, the probability of 2 electrons occupying the same state is exactly 0. That means no 2 electrons can ever have exactly the same quantum numbers in the same atom. But spin is itself a quantum number. So, if one electron has spin down and the other spin up, they can share the same orbital state. These, then, are the fundamentals that govern the chemical elements, the stuff of life and everything else in the sea, on land, and in the heavens. The rules are these. Each atom can be thought of as an ion, the nucleus plus the inner electrons, with one final outer electron needed to complete it. That electron goes into the next, lowest energy available orbital and spin state. For example, 2 electrons are permitted in the n equals 1, L equals 0 orbital. The first one completes a hydrogen atom, and the second, with opposite spin, completes the atom of helium. This completes an energy level, making helium chemically inert. The n equals 2 shell of orbitals has room for 8 electrons. The first, with L equals 0, makes a lithium atom. The next, with opposite spin, makes beryllium. Now room must be made in the periodic table for atoms with orbital angular momentum, quantum number L equals 1. The first is boron, followed by carbon. These states have slightly different energies, even for the same n, and as each element is formed, it chooses the lowest energy state available. Following that rule, the shell fills up with nitrogen, oxygen, fluorine, and finally, the chemically inert noble gas called neon. According to the basic rules of atomic architecture, the n equals 3 shell will have room for 18 elements, starting with sodium, then magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and the noble gas argon. But then a funny thing happens. Because of forces between electrons, the next lowest energy orbitals aren't the ones with L equals 2. Instead, a couple of slots in the n equals 4 shell get filled first, making potassium, and calcium. Each element displayed in this way has chemical properties similar to the ones above it and below it in the periodic table. No matter how complex it may seem, the startling fact is that all the complexities of the natural chemical world have been reduced to three fundamental building blocks: the protons and neutrons of the atomic nucleus, and the electrons bound to the nucleus by the electric force, and the quantum mechanical rules of the game. 3,000 years ago, there were four elements: earth, air, fire, and water. Then there were three: protons, neutrons, and electrons. Three little words to explain the nature of the universe. And yet, they weren't enough. Not that physicists could or would ever discover anything wrong with protons, neutrons,